You're now on video 4B of the 6-part series on creating breeding trial experiments. This one explores creating sparse designs. Feel free to watch these in order or skip to more relevant ones based on your needs. As soon as our entry list is finalized, we can now select our experiment design. On the far right portion of the screen, let's toggle to the new interface. Take note that when using the Design tab's new interface, you will not be able to regenerate the design in the Experiment Manager tool, as this feature is still under development. Alright, moving on, there are two testing methods used to allocate our entries in EBS, namely sparse and non-sparse. By default, the Design tab is set to non-sparse testing as indicated by None under the Across Environment Design data field. Let's switch to random so we can use sparse testing, which allows entries to be randomly distributed to different occurrences. The interface loads a new page where we can choose between generating the randomization in EBS or uploading a design file. To do the latter, toggle to Upload and click the Upload button. A template can be downloaded from the modal window, as well as a reference file containing information on the required headers for each design. Let's upload our file and pre-validate. The summary information will then be displayed, which also requires us to select the design for each parameter set. Parameter sets are groups of occurrences with specific protocols, which include the trial design to be used. Validate the design file and confirm. As soon as the file status is set to uploaded, we can view the design using the eye icon. If any revisions are needed, we can still delete these and re-upload new files. Let's now try generating the randomization in EBS. First off, we need to specify the number of experiment occurrences, including the number of iterations. Remember that the number of experiment occurrences should be equal to the total number of occurrences created in all of the parameter sets. Otherwise, we cannot submit it for randomization. Next, let's click Assign to load a page, where we can specify the total number of replicates per entry of the experiment, or total NREPs for short. This defines the number of seed packets that will be used to plant each entry. So this should account for all the entries and their replicates multiplied by the number of occurrences specified in all of the parameter sets. Simply put, the total NREPs should reflect the total number of seed packets needed when planting the experiment occurrences. Let's make sense of that with this example. Here, we want to create two parameter sets with these details. Let's look at our check entries first. Parameter set 1 has 2 occurrences, with each one requiring 3 checks that will be replicated twice. On the other hand, parameter set 2 has 3 occurrences, with each one requiring 3 checks that need to be replicated twice. That means the total NREPs for each check entry should be as follows. This successfully accounts for all the check entries' replicates, multiplied by the number of occurrences specified in all of the parameter sets. Let's reflect the total NREPs here, either one at a time or in bulk. Let's now move to our test entries. Parameter set 1 requires 25 test entries with a replication value of 1.4. This value means that the test entries need 1 seed packet for planting, and 40% of it need to be planted twice. So that's 10 tests replicated twice, while the rest of the 15 tests need only 1 seed packet. But because parameter set 1 has 2 occurrences, we multiply the NREP values by 2. In summary, we have these total NREP values for test entries in parameter set 1. Let's do the same for parameter set 2. This requires 35 test entries with a replication value of 2.2. This means that test entries need 2 seed packets for planting, while 20% of it need 1 more. So that's 7 tests replicated thrice, while the rest of the 28 entries need 2 seed packets. But because parameter set 2 has 3 occurrences, we multiply the nrep values by 3. In summary, we have these total nrep values for test entries in parameter set 2. Adding these to parameter set 1, we have these total nrep values for our test entries. Let's go ahead and supply these details in EBS. Let's click the back arrow button to continue working on our parameter sets. At this point, we can select the occurrence design. Unlike the upload option, randomization generated in EBS for sparse testing only supports the partially replicated design as of now. Additional fields are loaded that enable us to specify the design. Simply populate the rest of the fields for each parameter set based on the specifications we had earlier. As of now, the method of replicating test and check entries is limited to random. This means that EBS randomly allocates the entries in each parameter set. Lastly, the maximum number of plots should be equal to or greater than the sum of plots needed to plant check and test entries and their replicates. This value must reflect at least the minimum number of plots needed to plant each occurrence in a parameter set. For parameter set 1, we just need 41 plots. Let's save these to create parameter set 1 and move on to create the next. Again, take note that the number of experiment occurrences should be equal to the total number of occurrences created in all of the parameter sets. Otherwise, we cannot submit it for randomization. Let's create parameter set 2 using the same steps. For this one, we want to define the shape or dimension of the design. Finally, let's submit the parameter sets for randomization. Wait until the status of the request is set to randomized. Only those parameter sets whose field layouts were defined earlier will have the view icon enabled. In case we need to revise a successfully randomized parameter set, we can still do so by deleting the generated plot records. On the other hand, if randomization fails, we can view the error message to guide us in correcting it. Simply edit the parameter set or delete it to start again. That's it for sparse testing. Let's now move to the Protocol tab.